Hello everyone and welcome to the review session. I have just started recording as of 11:04. We are going to be going over sections 2.2 and section 2.3, and kind of the way I'm thinking of doing this is going over each part of the section in full and then going over an example. If you have any questions at any point, feel free to type it out in chat or to unmute your mic and just let me know, okay? So the first thing we're going to go over is just the limit of a function, like what even is a limit. Basically, it's where the function is appearing to go. So if you have a line that's not defined at one point, but the line looks like it goes through that point, that's the limit. We can calculate this algebraically by finding really, really small values near the point that we're trying to go to. We can guess what this point will be, or we can average out the smallest points that we have on either side to get as accurate as we can. So if we have 0.51 on one side and 0.49 on the other, we can average that out and get 0.5. We define a limit essentially by saying we have a function that exists when the number x is near the number a. So when we exist near that point, but it might not be at that point itself. We call this the limit. So we might say the limit of f of x as x approaches a equals L. We can only say this if we can make the values of our f of x or our y as close to L as we want by making our x closer to a, but not equal to a. We can't make it equal to a specifically because we don't even know if f of x can equal to a. Does that make sense? We don't know if we can actually be at that point. So why would we even use a limit? Essentially, we would use limits to find things like the velocity of an object at a specific instant of time. So at exactly 2 seconds, for example, which is practically impossible to calculate on your own without a vast array of technology, and even then it could be wrong. Or we can use it to find, for example, the slope of a line when we only have one defined point. These are the velocity problem and the tangent problem from section 2.1. I need to make sure I'm in the right chat so I can see when you guys have questions. Okay. Let me disable the online so I can hear you guys if you have questions. So I have my book open here so we can walk through an example if we need. This is the definition of a limit. So this is what a limit will look like. It looks like lim x arrow a, f of x is equal to L. And this essentially just states the limit of f of x as x is getting closer to a is going to be equal to L. So as x gets closer to a, f of x is getting closer to L. That's also denoted here. So f of x is getting close to L as x gets close to a. So this is the first example. This one wants us to guess the value of the limit of x minus 1 divided by x squared minus 1 as x gets closer to 1. We can essentially, so if you're looking at this, you would know that 1, when you plug it into this equation, will not give you an actual answer. It will give you a 0 over 0. And that means it is not defined. But because this is a limit, we're not looking at if it's defined at that point. We're just looking at which point does it look like it's getting close to. So what we can do is we can make these tables down here that usually will be correct to 6 decimal places for the values of x that get closer to 1 as long as they're not equal to 1. So our smaller and smaller values. And you'll see as we get closer and closer to the number 1, our values are getting closer and closer to the number 0.5, which means that our limit of x minus 1 divided by x squared minus 1 as x approaches 1 is going to be equal to 0.5. At this point, is there any questions? this should be review at this point for just this week. I know you guys had a lot more questions on 2.3, so we'll try and go through this part a little quickly. So this is just describing, like, as you can see, at 0.5 and 1, it does not exist. There's an open circle here, but the line looks like it goes through it. That's how we define our limit. There are a couple of cases where you might try and do calculations on a graphing calculator or on your own calculator to get really, really tiny values. But eventually, eventually what's going to happen is the smaller you get, the closer it's going to get to just giving you a 0. So as you can see here, they get smaller and smaller, and then suddenly, instead of getting a 0.1, we get a 0.000. And that's because calculators have, they essentially give false values, because if they get really close to a certain number, it will have too many digits. And it will essentially panic and give you a 0. So as you can see here, as it gets smaller and smaller, it looks like a perfect line when you have it as the interval -5 to 5. But as you get smaller, it becomes a straight line, -0.1 to 0.1. And then as you get smaller, it starts to look like it's oscillating, and then it suddenly goes to 0. And that's just because the calculator is not exactly sure how to do that. You can also look for that here. And that will explain more accurately why that happens. And this is actually something I wanted to bring up. You can find the limit of sine equations and cosine equations, but a lot of the time you'll find that as they approach certain numbers, like for example, as sine of pi over x approaches 0, it actually starts to oscillate really, really quickly. And because it's oscillating and it's never going to exactly approach or get near one number, we say that the limit does not exist because we can't tell where it's going to. So next we're going to go over one-sided limits. I want to double check. No questions? Okay. Again, at any point, feel free to unmute. So one-sided limits. What is a one-sided limit? A one-sided limit is looking at where the function is going to, but only from one side. So it's just like the regular limit, but we're only looking at one half of it. So we would denote this with a little minus or a plus next to our a value, but in the exponent spot. So how do we define that? We define them similarly to full limits or two-sided limits, but instead of saying as f of x approaches, we say as the left-hand or right-hand limit of f of x as x approaches a is equal to L. This relates to full limits because to make sure a full limit exists, we have to make sure that it can approach a from either side. So we need to make sure it can approach the same number from both sides in order to say it's approaching it at all. So we can say it approaches it from the left, approaches it from the right. If it approaches the same thing, then that line will go through that point. We need one-sided limits because without them we would not know if the limits match or if they do not exist. So for example, this one's a really good example, the Heaviside function. This is defined by this right here. So the value of h of t will be 0 if t is less than 0, or h of t will be 1 if t is greater than or equal to 0. That's, hold on, I need to drink water. That is shown here with the graph of the Heaviside function. So you can see here, as on the left side, as we get closer and closer to 0, as we get closer and closer to 0, we're approaching 0, right? So as x is getting closer to the 0 value, on the left side, the line looks like it goes to 0 and stops. But from the right side, as x gets closer and closer to 0, it approaches 1. It looks like it's going to 1, and then it stops. Because the left side is 0 and the right side is 1, we can say the limit does not exist. This line does not go to 1 fixed point, it goes to 2. So that's denoted here. We can see as x approaches 0 from the left, h of t is approaching 0, excuse me, and the limit of t as it approaches 0 from the right, h of t is equal to 1. So because these do not match, we say that the limit does not exist. So this is just the basic structure for that. So because of the definitions of one-sided limits, this is what I've been saying. The limit of f of x as x approaches a is equal to L if and only if the limit of f of x, the left-sided limit of f of x as x approaches a is equal to L, and the right-sided limit of f of x as x approaches a is equal to L. So it can only equal this value if both the left and the right equal that value. So this is another example that goes over it in a little more complex way. There's all these different points and all these lines. I suggest that if you are confused about this topic, to look at this example in the book, because it will go over it in more detail. It shows you 2 different left-sided and 2 different right-sided limits, and if they match the full limits. So at this point, is there any questions? Oh wow, there's a whole bunch of new people. Okay. All right. So for those of you who may have just joined, feel free to unmute if you have a question, and I'll do my best to answer it. So here we have the infinite limits. So first of all, what is an infinite limit? We know what a regular limit is, and we know what one-sided limits are. An infinite limit is a limit that actually does not exist because they do not approach an exact number. They continue to either increase or decrease forever. An infinite limit is a way to describe how it does not exist by telling us that the reason it doesn't exist is because it's approaching infinity or negative infinity. We can define an infinite limit as a limit that can be made as large as we like by making x as close to a as we like, but not equal to a. What we would say is the limit of f of x as x approaches a is infinity. We can replace this with negative infinity if it's negative infinity. And in this case, we can also say it is becoming quote-unquote large negative because the absolute value of the negative number is going to be very large. It's just a way to describe that it looks really big. This relates to vertical asymptotes because if a function has a limit of infinity or negative infinity, it will never reach a. If it will never reach a, but will continuously get close to a, which it is, we can define them as vertical asymptotes. Any limit, including one-sided limits, that equals infinity is a vertical asymptote. So if you have as f of x approaches, or as the left-hand limit of f of x as x approaches a is equal to infinity, but the right-hand limit of f of x as x approaches a is equal to 1, it would still be a vertical asymptote. It looks like it's getting close to a from the right, but on the left, it's just going all the way to infinity. So let's go ahead and look at an example real quick. So here we have 1 over x squared as our equation. And you can see algebraically, it gets really, really, really big really fast. So as we keep getting closer to 0, it keeps getting bigger. And you can see the graph right here. It's going all the way to infinity. And you probably would already know this because it's 1 over x squared is the function. But if you don't know this, this is a really good way of showing it. Um, you can see here as well that it's still going all the way to infinity, and we have this vertical asymptote in the middle where x is actually equal to a, because x is not defined at a. You can also do the opposite where it's negative infinity. And if we can get to the example that I wanted to look at. So this is a good example. So find the limit from the right as, wait, hold on. Sometimes it's hard to say the limit verbally, but you guys see this. The limit as it approaches this function right here from the right as x approaches 3, and the limit as x approaches 3 from the left of this function, right? So we can see, if we start doing it algebraically, we're going to see that from the right, it's going to become, excuse me, computer. Thank you. From the right, it's going to start approaching infinity, positive infinity. But from the left, it's going to start approaching negative infinity. This means that the line at x equals 3 is a vertical asymptote, even though they go to two different infinities. It also means that if you were to say the full limit, just as x approaches 3 from either side, you would just say it does not exist, because it does not approach the same infinity. You can see that here as well. But yeah, so that's kind of the basics of that. Does anybody have any questions at this point? And again, you can either unmute or you can type it out in the tutorial chat. Okay. I'm going to move on, but if you have questions, just feel free. So the next thing I have is practice problems for the odd numbers, 1 through 11. These are just really basic problems from 2.2. You can find them by going to the digital book in MindTap and going to 2.2 exercises. And you'll see that the odds have the answers. So you can explain in your own words what is meant by the equation. And you can say, is it possible for this statement to be true and yet f of 2 equal 3? Then you can explain. So I actually wanted to ask, at least for number 1, does anybody want to tackle this problem? So just to check for understanding, in case, even though no one's had any questions yet, I want to make sure you guys are understanding. Explain in your own words what is meant by this equation right here in the tutorial chat, okay? And then you don't have to explain this part, but just yes or no, is it possible for this statement to be true and have f of 2 equal 3?
Can you hear me?
Yeah, I can hear you.
Ah, yeah, shoot. I muted myself, so I wasn't, okay. So, it's true for, okay, yeah, it's true. It's true because, like, the surrounding graph can be approaching that point, but that point can exist somewhere totally different.
Exactly, yes. And for those who are in the recording and can't see the Discord, one person said, yes, it is possible for that point to exist and for the statement to be true, and another person defined the statement as x approaches 2, it is getting closer and closer to 5, which is also correct. All right, so here's 2.3. This is the one that's probably going to trip a lot of people up. All right, so calculating limits. How do we calculate a limit, and what are the different ways to calculate a limit? So first of all, we can use the limit laws. These are shown on the next pages. Something I wanted to point out is that the limit laws are very similar to the laws of logarithms. This is how I remember what they are. So if you have a log of f of x plus g of x, you can separate that out into log of f of x plus log of g of x. Same thing with limits. So feel free to review that. I have them all listed here so that you guys can look at it really easily. But I did want to go over specifically the direct substitution property, and I also wanted to go over a problem or two on the homework that we did, because I know that some people were having some issues. So with the direct substitution property, it essentially states that if we are defined at A, then we can substitute A into f of x. However, we need to make sure that we simplify as much as we need to, or as much as we can before plugging this in, because for some problems, it will end up with a 0 over 0, for example, if you just immediately plug it in. We can also, we'll also cover the squeeze theorem. So sometimes we can find that a limit is between two other limits. So if f of x is less than or equal to g of x, which is less than or equal to h of x, and both the outer two values, f of x and h of x, are the same, then we can say that all three are the same. That's called the squeeze theorem. So we can use this to calculate the limit when given these functions, or if we have an absolute value as the denominator. And then I have some practice problems here as well. But we're going to go ahead, and I'm actually going to open up my WebAssign. Actually, can I just do that from here? Hold up, I don't need to go to UTD. Because I want to go over this in more detail. This might take a minute though, because my computer is not happy that I'm recording and streaming. Can I go do this? Thank you. All right. So here's my homework. I'm going to use the practice problem function in it in order to show you guys some similar problems to what we've done. So I have to find the ones that I wanted to go over. I can't recall off the top of my head where they were. It's infinite limits. This is 2.2. Okay. So actually, let me ask real quick. Is there any specific problems that you would want me to go over from the digital homework?
Yeah.
All right, which one?
I think it's 30. 30?
30? Okay.
Yeah, I got the right answer on this. I just don't know how I got there.
Okay, so I'm gonna do practice another. And I remember this one caught me too. This one was actually pretty, oh, dang. Okay, we'll follow along with my own. This one also was difficult for me. But from what I recall, so I had done the watch it video. Basically, it's this is doing the limit law for the, where did it go? This one, number 3. So c of f of x is equal to c limit f of x. So you can actually take this 6x out and put it over here. And I actually wanted to ask, can you guys see this watch it screen that I pulled open? Nope, wrong button.
Prove that the limit as x approaches 0 of x to the fourth times, and we can multiply the inequality through by x to the fourth.
I am having some technology issues.
So the squeeze.
Right, okay. All right, that's okay. So I had to double check what I was doing. Can I open up? Okay. So with our problem, we have the limit of x to the power of 6 times cosine of 8 divided by x as x approaches 0 is what? To find this, we first have to recognize that cosine is an interval function. So the interval of cosine is -1 less than or equal to cosine of 8 of x less than or equal to 1, right? From here, we take our x6, which is being multiplied to cosine. Because we're multiplying it against cosine, we can multiply it against the 2 points of the interval. This is part of the squeeze theorem. So if we say -1 times x to the power of 6 is -x to the power of 6. We can say that that is less than or equal to x to the power of 6 times cosine 8 of x, or 8 divided by x, which is less than or equal to x to the power of 6 times 1, which is just x to the power of 6. So, I'm sorry, I forgot the next step. Give me just 1 second. Again, this was one of the problems that even I struggled with, because just looking at it intuitively, you don't really know what to do. But gotcha, okay. So we multiply it together, right? The next step is to actually use the squeeze theorem. So this wasn't even the squeeze theorem. This is just setting it up so that we can use it. So the squeeze theorem says that, let's say this first is f of x less than or equal to g of x less than or equal to h of x, right? So comparing these two right here, where this first one's f of x, second one is g of x, and the third one is h of x. We can use the squeeze theorem to say if f of x and h of x equal the same value, then the center equals the same value. To do this, we would set up the limit. So limit as x approaches 0 of -x to the 6th is equal to what? And then we would do the same thing for the following, for the last value. So our quote unquote f of x and our quote unquote h of x, right? So if we plug in 0 to -x squared, or -x to the power of 6, what would we get as our answer? This is actually a question.
Zero.
Yeah, we get 0. If we plug it into positive x to the power of 6, what answer do we get?
Also 0.
Yeah. So from here, because both the quote-unquote f of x and h of x are the same, we can say that the center one is the same. So here we can say the limit of x to the power of 6 times cosine 8 divided by x is equal to 0. And that's how you get this answer. Does that make sense?
Yeah, thank you.
You're welcome. Go ahead and save that. Does anyone have any questions on another problem on here? I know I wanna do that words. I want to go over problems that you guys have with the homework first, or questions that you thought were a bit hard, before doing this, like, problems that I think that we should go over, like 35, because a lot of people were having issues with 35. But I want to make sure there's not any that you guys have that are difficult. Or any questions, period. Like, is there anything specifically that is confusing to you or doesn't make sense? I know I kind of went fast. I was worried that we weren't going to have time with both sections, so. All right, if no one else has any questions, I'm going to go ahead and just do 35 real quick. So with 35, I just want to explain. So I had, can I do practice another? Yes, I can. So we have, if the limit of f of x minus 4 over x minus 1, as x is approaching 1, is equal to 8, what is the limit of f of x as x approaches 1? So the first thing to do here is to simply take this equation and solve for f of x. So all you would do is you would multiply both sides by x minus 1 to get rid of this division. You'd end up with 8x minus 8. Then you would have f of x minus 4 equals 8x minus 8. You would add 4 to both sides, and you'd have f of x is equal to 8x minus 4. Then all you have to do is, because we're approaching 1 here, plug in a 1 into the equation for x. So 1 times 8 is 8, minus 4 is 4. So f of x would be 4. And you can even show the solution on the practice problems, which is really nice. It has a whole PDF for it. Okay, that's neat. So this kind of walks you through the exact thing that I just spoke through. You just multiply both sides. They did this a lot more complicatedly. Ignore that. You literally just have to solve for f of x and then plug in the 1. So that's just using direct substitution property. But yeah, at this point, if you don't have any specific questions, you're free to go. If you do, I will be here until noon, possibly slightly after if a lot of people start having questions, just to walk through some stuff. All right. I'm going to keep recording just to make sure that if anyone has the same questions, they can see it later as well. And I can, like, re-go over stuff if you need me to and all that. Of course. What would you do if a function approaches a value from one side but not the other side? So if a function is approaching a value from, there's nothing on the other side, in that case, the limit would not exist. So that's because so essentially the limit would not exist, because if it's only approaching from one side and the other side does not exist, then the whole thing cannot exist. Does that make sense? So if the line is only on one side, yeah. I'm also going to say for those who might be on the video later, feel free to @ me or DM me on Discord, and I will help you out as best I can. Oh, thank you for this review session. I was busy taking notes, so I didn't talk. That's totally okay. Oh, they left. Of course.
Thank you. I appreciate it.
Yeah, no problem. Yeah, I'm just gonna be chilling here until either everyone leaves or we have if we have any other questions.
Yeah, thanks for the review. It's nice.
Yeah, no problem. Next time I'll
Bye.
probably be able to do it slower.
Okay.
All right, it looks like everyone's left, so I'm going to go ahead and close out of my Google Chrome, and I'm going to go ahead and end this recording. So thank you everyone so much for watching. I hope you have a good day and understand what I went over. Again, @ me if you need anything.